Okay, folks, we'll go ahead and get back started again. A continuation of our discussion from the SDN track. My name is Scott Hoch. I'm a founding member of the Rocky Mountain V6 Task Force. I was chair for a long time, then Chuck Seller was chair, and now Agni Amitev, who you've heard this week as the chairman active. I'm still involved in the group. I'm also part of the Infoblox IPv6 Center of Excellence, and I'm a Chief Technology Officer for GTRI, Global Technology Resources, Inc., system integrator, headquartered here in Colorado, but we've got offices and do work around the country and even a little international work. Today I'm going to talk to you about OpenFlow and IPv6, two great tastes that taste great together. So as all rights reserved, the Hershey Company. But as you enjoy your Reese's Peanut Butter Cup, we'll talk about these two great tastes that taste great together. I'll go over a little bit of software-defined networking background. I know those in IPv6 technologies may not know as much about SDN, so we'll go over a little bit of background, but I know you've heard some things about SDN yesterday's session. We'll talk also a little bit about OpenFlow and what that is and how that works with IPv6. We'll talk about its history and lineage and when did OpenFlow get IPv6 capabilities. And then we'll talk about specific demonstrations, implementations of OpenFlow 1.3, and then I'll do a demo which involves OpenDaylight, MiniNet, and OpenVSwitch, and some questions and answers. So software-defined networking is an approach to networking that separates the control plane from the forwarding plane to support network virtualization. It's a new paradigm for how we approach networking. In the past, we've had control plane local on a router that makes local decisions about forwarding traffic. We use routing protocols to share route information, reachability information between adjacent neighbor routers, and they form adjacencies and share topology information and take those routes, instantiate them into a forwarding information base, and then they forward packets from end to end based on this, the destination address of the packet. And every router kind of used the network from its own particular knothole and understands only the global routing table of the routes with which it's been able to hear from its neighbors. So the routers and network elements, network devices lack a global view of everything that's happening in the network. Each router has a management plane, a control plane, and a data plane in and of itself. But with software-defined networking, we're separating these functions, particularly the control plane from the forwarding plane, to see if we centralize the control plane into a system that had a global view of the network, maybe it could make more intelligent decisions about forwarding traffic, and or could create traffic paths or forward traffic in other ways or based on other policies that we are limited in doing today with modern routing protocols or modern hardware systems where decision is made locally on the network device. And so at a high level, this separation creates separation from what's called a controller device from the network elements. The network elements may also operate in a hybrid way where maybe they have some bit of a controller or control function on them, but then there is an overriding controller that has that global view of everything that's going on and has that central policy configuration. So this controller uses a southbound API or a southbound protocol to communicate flow information to network elements to tell them how they should populate their tables, their flow tables or their tables or their policy tables. You can think of it like a access list where the switch or the network element would go through its table or list of flows one item at a time to see which is the best match for the packet and then take that appropriate action. Sometimes it might be drop, sometimes it might be forward, sometimes the action may be flood, sometimes the action may be modify the packet and then send it on, or what have you. There's a variety of different actions. And so the controller is this central place for making decisions. The controller can be highly available. You can have multiple controllers for a network and the controllers synchronize their information between themselves. You can have multiple controllers for different tenants in a multi-tenant data center environment. But the controller is where a lot of the configuration takes place and where the southbound protocol is originated from. If a network element gets a packet that it doesn't know how to handle, it will send it up to the controller and say, hey, I need some assistance here. I don't know what I should do with this packet. Please give me some advice. And the controller will do that function. The controller also then can create a northbound API or a northbound protocol that allows some other higher level functions to interact with it to then create some more advanced policy. Or maybe the creation of a particular virtual server or workload or virtual machine or new compute instance or storage instance may then request from the controller through the northbound API services from the network. And so we have this SDN layer kind of at the top, which is really the high level view of requesting from the application view or from the services view what's required from the network. The controller layer implements some of that policy by talking down to the network elements about what's needed in the network. And so we're aggregating kind of this network for forwarding decision intelligence and putting that into the controller rather than leaving that up to the distributed nodes. So some of the benefits we might get from an architecture like this is that we can maybe forward packets in ways that we couldn't before. Maybe we have greater customization, or we have greater ability to create policies. We have greater span of control and analytics. The controller has that global view, as I've said. Maybe we could get greater intelligence of the network and understand traffic flows and which traffic paths may be more heavily loaded than others. We would then have knowledge of alternate paths that may be less loaded that might still meet the application's requirements for end-to-end connectivity. We may, in the end, have better improved application performance or have the ability to scale up or scale down. Maybe it would give us simplified IT administration. I mean, essentially, server virtualization has transformed over the years, where before every operating system had to be loaded onto a separate physical hardware device. Now servers have moved to virtualized server environments. Virtual machines can be moved and cloned and copied and motioned between data centers, and they've gotten a lot more flexibility, easier to stand up a dev, test, production environment in a virtualized environment. But with networking and with storage, we have tiers of storage, we have flash-based, we have all kinds of virtualization and a lot more software in the storage array that gives a lot more rich features for storage virtualization. In the networking industry, basically our transformation is we went from Telnet to SSH in the last decade. Every network element is still managed individually. So if you had something you needed to do to a broad range of network elements to change a behavior, it has to be done manually. Quality of service settings are a common example. Everyone sets their quality of service settings in an enterprise network, let's say, to prioritize handling of traffic that's marked with the type of service or diff-serve code point EF to prioritize voice traffic, let's say, on the network. But let's say maybe there is an application that's maybe more important than voice, or a video session that maybe is actually more important than voice that you want to give preferential treatment to on a particular day. You have to go and reconfigure all these network elements manually to get that to happen, and then when that event is done, then go and touch all those devices again. Difficult to, there can be some scripting and stuff, but to achieve some of these goals, some of these requirements, but maybe SDN offers a way for simpler administration and ease of configuration. Also, SDN may have the ability to say, if it's Tuesday and this is happening on the network, then give more traffic volume to these types of applications, or if it's the end of month or end of quarter, then we have this type of a traffic profile. It could be limited based on time of day, or maybe the controller could have the type of logic to be dynamic and say, if I get to 70% threshold on this link, then I route traffic in this other way. I trigger automatically that, oh, it must be backups are happening. I don't need to know that backups happen at midnight. Backups could start at 11. The network would just automatically detect that, oh no, backups are starting. So maybe SDN could support rapid enhanced multi-tenant cloud services deployments and offer opportunity, to network in other ways. Many use cases, as I've just described for SDN, creating network services that are complex or time-consuming to implement, network segmentation, multi-tenancy, doing a tap aggregation, kind of creating a system like ER-span or something like that. WAN traffic engineering, deciding what's the optimal traffic path. Do I go across the corporate MPLS network, or do I take the extranet IPsec VPN that's created via maybe, let's say, DMVPN over the internet as an alternate path? Things like that. Network and SDN facilitates network programmability. Also, with modern networks, traffic is forwarded based on a destination address in the packet based on longest match. But maybe we wanted to have longest match and check if it contains IPv6 mobility header, but not if it's a fragmentation header. Maybe we would want to have Boolean logic to match certain kind of traffic, and with an access list or multi-line QoS CLI config in a Cisco iOS device, it's very top-down, if then else. We don't have the Boolean logic that may facilitate forwarding packets in some ways that we may want. SDN could do that because it's at a higher level. So OpenFlow is a protocol that supports software-defined networking environments. It's the southbound communication from the controller. So it's not the northbound. The controller talks OpenFlow down to the network elements. The network switches then talk up to the controller with OpenFlow when they don't know how to handle a particular packet. So OpenFlow is that protocol that creates the flow tables in the switches, but also lets the flows get dynamically created based on policy from up to the controller. Uses a legacy TCP port. The new port is 6653 and can be encrypted with TLS. So OpenFlow evolved from this clean slate program, which was research that was being done at Stanford University, which clean slate basically is this idea that let's wipe the slate clean and let's start over thinking about how we do networking. How would we change things if we could start over again? And reimagining networking and starting over kind of conceptualized this concept of a controller and this OpenFlow protocol. The Open Networking Foundation was formed in 2011 to formalize the protocol as a standards body that could help ensure some interoperability between groups and vendors' implementations of OpenFlow. There was a switch specification in February of 2011, and different versions started coming fairly quickly. And in the 1.1 range, the IPv6 started to become a consideration as a requirement, but didn't end up getting implemented until 1.2. There's definitions and fields to match particular fields in an IPv6 header. And so with OpenFlow version 1.0, there was just a 12 tuple, or 12 different characteristics of an IPv4 packet that could be matched. And then based on that, there could be counters and actions. There's a variety of actions that were created, and this was defined in the specification. In 1.2, now they're looking at things inside the IPv6 header. So version, traffic class, flow label, addressing, payload, next header, and hop limit. And also matched unicast and multicast and ICMPv6 type and code. In 1.3, it started to extend that capability and look at the next header value. The next header value is what indicates the header that follows the IPv6 header, which is the extension header. So as you know, there's maybe a layer 2 header, maybe that's an Ethernet 2 frame. You have an IPv6 header, and the next header value is 43, well, or whatever equivalent in hex would be. That would indicate that what follows is a routing header. If the routing header had a next header value of 44, then what would follow would be a fragment header. If the fragment header had a next header value of 6, then it would be TCP. And if packets are TCP or UDP or ICMP, what ends is either upper layer, payload data, or that's just the end of the packet. So TCP headers don't have a next header value. You can think of this as a linked list or a chain of headers that ends in a null that says that's however big the header structure is. And middled boxes just look primarily at the IPv6 header or maybe a routing header, but the destination node then parses all of these headers to then formulate and reconstruct the whole packet, reassemble any fragments, and then hand it up the IPv6 stack. Well, OpenFlow 1.2 allowed you to match on header fields. OpenFlow 1.3 allowed you to match on extension headers. So now we have a lot more things in OpenFlow that we could match on here. Oh, and MPLS labels and things like that. I mean, it got extended in other ways too. And now we have a lot more different kinds of functions and the ability to have multiple tables that refer to other tables, kind of a hierarchical nature and things like that. So it gets extended, and also OpenFlow 1.1, 1.2 weren't as widely supported. 1.3 was really a stability release for a lot of, for the Open Networking Foundation. And so a lot of vendors would either support 1.0 and not have any IPv6 support, or they would support 1.3 and have IPv6 capabilities. There is also OpenFlow version 1.4.0. Here's all the different kinds of things defined in the specification that can be matched on. It's kind of a blow up of that. But you can see that there's different kinds of packets that can be matched on based on the headers and so forth. And then the extension headers and different types of extension headers here can be matched on. Some vendors do support OpenFlow 1.4 today, but the majority of vendors would either support 1.0 or 1.3. So there's a big list now of companies and organizations that support OpenFlow 1.3. Probably 6 months ago, this list was maybe half this size. So definitely you see an expansion of companies that are, and open source controllers that support OpenFlow 1.3. And then switches, many of which are switches that Jeremy mentioned in his presentation, or maybe white box switches, may operate in an open vSwitch way or use Quagga or other methods, but then other white box type switches could use the OpenFlow protocol to be controlled. So you could have a network that maybe is mixed with Open vSwitch and Pika 8, and maybe uses a different kind of controller or something like that. So one controller, an open source controller, could be controlling a variety of vendors' equipment, and like Jeremy said, then gives that end user company a multi-vendor, vendor-independent type of deployment where they're not locked into a particular brand of hardware switch. So wide range of companies that support OpenFlow 1.3. There's a gigantic list of companies that support OpenFlow 1.0, and I apologize if I've excluded any company that supports 1.3 and I didn't put them on this list. This is as best as I could do with the research I had of what their support is. So I'm going to show you a demonstration in my computer here, all with software, because it's software-defined networking. I'm going to show you an entire network based out of software. I'm going to show you an environment that runs on my laptop. So imagine this is my laptop. And inside of it, well, I have a virtual kind of network here. I'm going to run this open source utility called MiniNet, which is just a way to create a topology of virtual switches or network elements. In MiniNet's case, it's Open vSwitch is what gets built. And I'm going to use the OpenDaylight controller as an open source controller to make changes to that network. So, and then this all runs in VirtualBox. So let me go into each one of these elements of the environment a little bit more, and then I'll show you the configurations. So Open vSwitch is a multi-layer virtual switch that's implemented at the hypervisor. So you heard the presentation yesterday about network functions virtualization from Don Clark, Cable Labs. This is essentially that concept. We have an Ethernet switch that's embedded in the virtualization layer of a piece of, of a computer. It could be a desktop laptop, it could be a server, it could be any kind of virtualization system could implement this Open vSwitch, and that switch could then decide which virtual machines or compute instances are connected to which VLANs or ports on that virtual switch. So just like Jeremy showed us an example where there were virtual switch ports, this would have virtual switch ports. And you could put some virtual machines into one VLAN, other virtual machines into another VLAN if you wanted to segment PCI data separate from HR data or something like that. You could create these virtual switches, and you could join these virtual switches between servers using tunneled protocols like NVGRE and VXLAN and other protocols like that. Or you could just send them to a hard switch upstream or to a firewall or something like that in a .1Q trunked interface. Two methods of configuring Open vSwitch. Well, you can configure it directly. But you could use Open vSwitch database, OVSDB, JSON, or you could use OpenFlow. And so the Open vSwitch is what I'm demonstrating here today because it supports OpenFlow 1.3. And you could get a free copy of Open vSwitch from openvswitch.org. So MiniNet is a method, a free open source tool that allows you to create this any kind of variety of network topology running in a kernel switch and application code on a single machine VM, and it's easy to get running in just a few moments, and that's why I use it, because it's very easy and I like simple. And MiniNet version 2.1.0, which is the current version that I'm using, and it's the current version that's available, uses Open vSwitch, OVS version 2.0.1, which supports OpenFlow and OVSDB. And you can download it from mininet.org. OpenDaylight is the controller that I'll be showing you today. OpenDaylight is an open source controller that's the OpenDaylight project produces. The OpenDaylight project is many groups of both open source contributors as well as commercial organizations. Cisco, Brocade, other companies collaborate on this and produce an open source version of a controller. It has northbound APIs, a REST API. I know it's kind of hard to see here, it's a little washed out, but there's a representational state transfer API northbound. And then inside of the controller, southbound, it can speak OpenFlow 1.0 or 1.3 southbound to the network elements. It could also talk OVSDB or netconf downstream. So there's a services abstraction layer, and that model-driven service abstraction layer allows the controller to talk to different devices in different means, southbound, and northbound, the REST API can be communicated to by applications and services or with a script that you write or something like that. So key to our focus here, we're going to focus here on OpenFlow 1.3. And I'm going to be showing you the Hydrogen release of OpenDaylight, which came out earlier this year. And there's a Helium release, which is coming out in 1 week. So they're just finishing up the codes. There's now advanced release candidates available. And on September 29th, so here in just a few days, there'll be a Helium release. But since I'd already built this and I know it works with Hydrogen, we'll just focus on this. But there's a bunch of new features. You can go to OpenDaylight.org, and from that website you can see what are the new features that are coming in the Helium release in just a few days. Okay. So I'm going to start this up in my environment. Running VirtualBox. I have my OpenDaylight controller that has this IP address and my MiniNet, which has this IP address. And inside MiniNet, I'm going to create this topology. So it's kind of a simple topology. It shows a network. There's switches that are joined together. There's these virtualized hosts, which are kind of very small Linux-like hosts that we can interact with and generate traffic between to simulate networks. And I've got a host here that is acting like a router. So I've got some hosts which are just hosts. I've got hosts that send traffic in and of a switch. I've got hosts that can send traffic between switches, so you'll see how flows just instantly get created across switches, and then we'll see a host that's performing like a routing function, an IPv4 and IPv6 forwarding, and a host over here, and these are the ports and IP addresses. So just so you know, we can come back to this picture here, but this 10 network, so the 10 network is kind of on this side, and the 20 network is on the right-hand side, so 10.20.0.5 is host 5, 2001 DB8 20:5 is 5. So 4 bridges the 10.20 network and the 10.10 network. So he's 10:4 on this side and 20:4 on this side. And forgive me if I use terms like 2001 and 20. I do know these are hexadecimal numbers, so, not decimal numbers. So these are the ports and stuff. You don't need to know all of these. This is more for my debugging purposes. So I guess I'll just go ahead and start in on this setup. So what I do is I just downloaded MiniNet, the OVA file from mininet.org, and I imported it and I started it. I downloaded the Fedora 20 version of the OpenDaylight controller, and I downloaded it and I started it. And when you start them up, you end up in an ODL login. ODL is the username and password. I have config. So you see 192.168.56.106, that's my OpenDaylight controller. MiniNet is my username and password. And right now I don't have anything running here, I just have an Ethernet 0 and a loopback. So those are my addresses here. So that's all running in VirtualBox. So now we're kind of done with that. So what I've done is so I apologize if this is going to get a little crazy. I'm going to be typing a lot and showing you some different screens of things. I have two sessions here where I've connected to my ODL, 2 sessions here where I've connected to my MiniNet VM, and I'll show you why I'm using 2 in a little bit. So what we're going to do is when we have OpenDaylight running, so we're going to connect here, we're going to go into CD into ODL/OpenDaylight, and we're going to run a command that's going to start the OpenDaylight controller. So sudo run.sh virtual ovsdb-of13. So we're going to tell it start the controller, and I want to force OpenFlow 1.3. Okay, so we'll start that. Takes it a while. I could just show you a cake that was fully baked, but instead I'm going to show you the process of the ingredients going into the cake. So that's going to run for a little bit. And I need the controller to come up first before I start MiniNet, because if I start MiniNet and the controller's not ready, the switches are going to try and talk to the controller, and they're not going to be able to. So I start OpenDaylight first, and then start MiniNet second. So when I get here, I get an OSGI. I do an SS command. Okay, I think it's still starting. So I do SSOVSDB, and I see that I've got OpenDaylight version that I'm running. So I see that I have OpenFlow plugins here running. If I do a print nodes, I have nothing connected to the controller at this point. Okay. So now on MiniNet, there's a couple different ways to start MiniNet. You can just start it by doing sudo MiniNet, and type in something. Well, that would clear the config, but you can start it with just a command line. You could run a script, a Python script, which would then start it. So, like if I created this topology 3 switch 5 host topo.py. So in the custom directory, there's a custom directory and then an examples directory where there are example custom topologies. So I'm running a custom topology because I have that host 4 that's acting like a router. So I'll show you what it would look like if I was to run a custom topology. So here's a custom topology example. I have basically I'm going to create a topo called topo, a simple topology. I'm going to define and create this network. I've got a left host, a middle host, a core host, and I name them H1, H2, H3. So I'm calling this function self.add host, and so this is here. And then I add links. I connect left host to left switch, left host 2 to left switch, middle host to middle switch, core to core, and so I just kind of name them that way. I could also, so this is what I'm going to do. I could also create an example topology. I know I've used the same name, but an example topology actually is a Python script which would start the network, and I would call the controller. So I specify the controller that I'm going to use and the port that I'm going to use, because that's the port for OpenFlow. I can create hosts, I can create switches, I can create links with net.addLink, and then I can also run commands. So on H4 I can give it a v4 address on that port, I can give it a v4 address on that port, I can sysctl, syscontrol, set up IP forwarding, I can set up all my routes so that the other hosts in the network route packets to H4, I can add IPv6 addresses to my hosts and things like that, and then add v6 routes and things like that. Okay, and then start the network and then stop it when I'm done. Well, since I need to force OpenFlow 1.3, I don't know how to do that in a Python script, so I am going to start this kind of the old-fashioned way. So I'm going to call sudo, because I'm not root. I'm going to do sudo MiniNet, and I'm going to call my custom topology. I'm going to say topo is just my topo. I'm going to say controller remote 192.168.56.106. That's the OpenDaylight controller. I want to run it on this port, and I want to specify OpenVSwitch and OpenFlow 1.3. So I do this on purpose because I want explicitly OpenFlow 1.3 because I'm going to be showing you v6 stuff. So here it creates my network. It builds the environment. I can do nodes. Where am I? I can do nodes. I see my nodes. I can do net, and I see my net, and I see which host and ports, and this matches the diagram that I had on the other side. I can do dump, and I can see addresses, but the addressing now, you can see that the addressing doesn't match what I really want to have happen. I can do, oh, I did a dump, and I can do dpctl dump flows, and you see I have no flows. But then also, it's not doing exactly what I want, because I want to force these switches to be OpenFlow switches. So I come back over here to this screen, and I'm going to do a sudo ovs appctl command and look at my OVSDB server version. I'm going to see that I'm running OpenVSwitch 2.0.1. I'm going to do a sudo ovs vsctl show, and I'm going to see that I'm running an instance. I have a bridge called S2, a bridge called S3, and a bridge down here called S1. I'm communicating on port 6653 for OpenFlow, and then these are the ports that I have configured. If I check my remotes, I see that I'm running OpenVSwitch. If I look at my bridges with this command with the ovs vsctl list bridge command, I can see that my bridges are not running, the protocol is empty here, and the data path type is empty here, meaning that these switches are still running OpenFlow 1.0. So I need to force them to run OpenFlow 1.3. I can check the controller, and I can see from the controller perspective how things are working. So what I'm going to do, I'm going to paste in 3 commands here real quick, and I'm going to set the bridge sudo ovs vsctl set bridge s1 protocols equals OpenFlow 1.3. Now, when I list the bridges, now you see that it says protocols OpenFlow 1.3 here. So I forced them to be OpenFlow 1.3. Okay. Oh, and I'm going to, just to clean up, just in case I had any leftovers, I'm going to do an OVS dpctl del flows. I'm going to delete any flows that might have hung around. There might have been an OpenFlow 1.0 flow that got instantiated. I want to nuke those flows. I only want to build OpenFlow 1.3 flows in this switch environment. So now I'm going to check. I'm going to do a OVS OFCTL dump flows S1-O OpenFlow 1.3, and I see that I'm running OpenFlow 1.3, and I have no flows. And then I'm going to, I guess, list the bridges, and I see I'm OpenFlow 1.3. Okay, looks great. Okay, now if I go back to ODL, and in the OSGI interface here, now I say print nodes. Now I see I have 3 OpenFlow switches, both with the MDSAL. I have OpenFlow :1, OpenFlow :3, OpenFlow :2. I've got my 3 OpenFlow 1.3 switches running now. Okay. So what I'm going to do, I'm going to run Wireshark, because we like Wireshark. I'm going to start that up, and I'm going to capture on my, let's see, I'm running a VirtualBox host-only network here. I'm going to start capturing traffic, and I'm going to be capturing a bunch of stuff talking between 106 and 107. These are a lot of OpenFlow. You see that there's a lot of OpenFlow packets. I haven't done anything between the hosts. They haven't even sent their first little packets yet, and they're already communicating OpenFlow. And in here I can say OpenFlow v4, and I can see that I am getting OpenFlow OpenFlow v4 in Wireshark looks at OpenFlow 1.3. If I put OpenFlow v5, then I would be looking for OpenFlow 1.4 flows, so it's kind of one back. Kind of like multicast listener discovery versions equating to IGMP versions. One back. So OpenFlow v4 is _v4 is looking for OpenFlow 1.3 flows. And you can see that the destination port here is 6653. So I'm capturing some flows. Okay. Just to start that kind of in the background. Okay. Thanks for bearing with me. And this is going to be kind of the tedious part, because I have to then put addresses on everything here, and I have to do it manually, maybe because I don't know how to do this. Like the Python script method doesn't work now that I'm doing this method of launching OpenFlow and OpenDaylight to force OpenFlow 1.3, so bear with me. I've got this all copied to clipboard. Oh, and I also can't just dump all these commands in all at the same time, because the MiniNet CLI won't allow me to do them all at once. So
Scott, if I can ask a question without interfering with your flow.
Yeah, you could.
The status of where you're at right now, it sounds like you have all your devices up. Is there a control plane communicating between those devices?
They are, and I was capturing with MiniNet, or with Wireshark, I was capturing the southbound traffic between the controller and the switches. And you saw those OpenFlow v4 packets there. Yes. So once we put some IPv4 and v6 addresses on these virtual hosts in the MiniNet environment, then we'll be able to generate some v4 and v6 traffic, and then we'll be able to build some flows here. So I apologize. This is taking me a little bit of time here, but I've got it. We're almost there. Yeah. So what we've done is we've started up our OpenDaylight controller. We have started up MiniNet. We forced MiniNet to talk OpenFlow 1.3, and now they're communicating. We're just changing some of the IPv4 and v6 addresses on these virtual hosts in the topology so that they're exactly the way we want them to be. And then I'm also adding v4 and v6 static routes, so all these hosts kind of look towards host 4 as the router in the environment. So, okay. So now I have all this stuff put in here. So now if I did h1 if config, I'd see that h1 eth0 has the right v4 and v6 address. If I did h1 IP route list, I'd see his routing table. If I said h4 IP route show, I see that he has 2 connected routes. I can do an h4 route, and I can do an h4 route -6, and I see h4's, the host that's performing routing, I see his v6 routing table. Okay, so now let's look at the flows. So I'm going to come back over to this system. So I don't have any flows yet. They haven't created any traffic. So now what I need to do, I need to actually ping between these hosts. And the pings, what these pings are going to do is they're going to start the ARP process. And these switches that I've set up right now in MiniNet and with OpenDaylight, they default to being learning switches. So they work just like a regular Ethernet switch, where they learn what MAC addresses are off of each port. So that's what the switches need to do now. I need to generate some traffic from the hosts. The traffic and these pings are going to fail because the ARP and the MAC addresses haven't been learned off the switch ports. But as soon as some of these hosts start to learn some packets, this is going to fail. It doesn't know the MAC address of who I'm going to ping. So I just need to generate like a few packets from these hosts. I generate a packet from H1, I generate a packet from H2, I generate a packet from H3. Whoops. Got to wait for the timeout here. Generate some packets from H4. Just wait just a minute. This is kind of tedious. But what's happening is the switch is starting to then, these switches are starting to learn about what's in the environment, what's connected. And right now, they're generating lots of communication between the Open vSwitch and the controller. There's lots of OpenFlow v4 communication, or OpenFlow 1.3 communication taking place in that southbound communication as these switches are building their flow table. Okay, so now I'm in pretty good shape. Now I can just generate like a whole ton of pings. Okay. There's still a few MAC addresses that haven't been learned yet. So now, you saw those pings went by really fast now? Okay, so now we have flows. We have v4 flows because I'm creating v4 pings. So we'll come over here, and instead, before I didn't have any flows, now I have a ton of flows. So when I do sudo of obs ofctl dump flows s1-o openflow 1.3, I'm only interested in the 1.3 flows. Now I see a whole bunch of flows here in this environment. Now I can generate some IPv6 packets between these hosts as well, and we'll see that I'm going to build, v6 flows. Okay. Never demo, never demo, never demo. Teach myself that next time. It's going okay so far. So you don't have to write down all these commands that I'm typing in. You'll be able to watch the replay, and what the replay is you will see exactly what I'm typing. So you'll be able to see the scripts. And then also, I provide my contact information after the event, and if you want to know the commands that I'm typing, I'll share these with you and stuff like that. Also, if any of you are doing your own experimentation with Open vSwitch and MiniNet and OpenFlow and OpenDaylight or other controllers, I would be interested in collaborating with you too. So let me know how we can work together. I'm just kind of showing you some stuff that might hopefully speed up your getting going. Okay, now my v6 pings are going pretty good, and I'm able to ping kind of across the network now. See, I'm able to ping from H5. Where did my pointer go? Okay, here's my pointer. Where did my pointer go? Okay, so I'm pinging from H5. I'm doing a ping 6, count of 1, to host 2. So this packet went all the way through host 4. So to prove that to you, I will do a traceroute. So on these little virtual hosts, I can do H1 traceroute 6 -D, because I want to suppress DNS. Resolution for each hop, 2001 db825. And we see that it goes through 4 and then to 5. If I do a traceroute in the opposite direction, I see that I'm going from 4 and then to 2. So I have end-to-end connectivity through this network, and I will show you the OpenFlow flows. I mean, there's a lot of flows here. But, you know, on S3, so if I look at just the flows on S3, I see I've got, you know, just a couple of flows, 2 flows. I've got the flow from H5 to H4, and I have the flow from H4 back to H5, because the switch number 3 only has 2 hosts on it. So I have 2 flows. Okay, so I can do some other OVS, VSCTL. Okay, let's see. Okay, so now I'm going to show you in the web interface, I'm going to connect to OpenDaylight. So you just HTTP to the IP address, v4 address, or v6 address of OpenDaylight, port 8080, and I'm going to connect to OpenDaylight. I like to use default passwords, so it's admin, admin. And I'm going to show you the graphical interface. Now that we've built some flows, and OpenFlow knows the topology now, it now knows some hosts that are in the environment here. So I can see, I can rearrange this and make this look a little prettier, make it look a little bit more like our diagram here. Okay. What did I do here? Okay. Sometimes, okay. I'm not advocating that this is a great graphical interface, and you often have to hit refresh a lot with OpenDaylight. It basically has 3 tabs here. Devices, and I see the topology here in this window. I can see the devices that each run, and I can see how many ports each of them have. I can see the ports, and I can see ports here, and the ports get discovered here. I can see, I can create static routes down here. I've got a connection manager. I can create span ports. I can create other subnets here. In the flows category, I can create manually configured flows. And in the troubleshooting section, I can click on a switch and see the flows down here. So, okay, I can see the flows down here. So flows have, but I'm not seeing, you know, source and destinations. There's just stars here. This isn't a great graphical interface, but you know, you can see that there's an interface here, and I've discovered an environment that's taking place here. Okay. So now I've shown you that H1 and H5 and H2 can talk across the network through the environment. Now what I'm going to do is I'm going to use, in this environment, I'm going to create a flow. I'm going to add a flow with an open vSwitch command. So I'm kind of adding the flow down low flow. So OF CTL add flow S1 priority. By default, all the priorities of most discovered flows are priority 1. I'm going to give it a priority of 500, so it's very high up in the table. And the tables are matched top down, higher priority first, lower priority second. The data link type is 86DD, which is Ethernet type for IPv6 packet. I'm going to match traffic that's sourced from 10::2, destined for 20::5. My action is going to be drop. So now H5 can't ping H2, drop in the traffic. I can go in and in here I can do troubleshoot. I put that in switch 1, flows. Okay, so I see my flow here, and the reason it's at the top of the table is because the priority is 500 over here. So I have a priority, and if I go further down here and I look at, gosh, click on this, it should show me that the, flows, this is dropping the traffic. And I see counts. So I saw a packet count. I saw 1 packet count. I generate another ping. Come back here. Flows. Takes a minute here to get refreshed. Flows. 2. Now I got 2 packets. 2 packets have been dropped. So, okay, so that works, right? And then on S1 over here, I can dump the flows for S1, and I see right here at the top, I see my flow here that says priority 500, IPv6, from this source to this destination, action drop. Okay. So let's do an open vSwitch command to delete that flow. So I'm going to, okay, sorry. I'm not going to delete the flow. What I'm going to do is I'm going to create another flow with priority 501 that's on top of it that says allow it. So now when I ping between H5 and H2, I get there. Now if we go back and look at the GUI and I do troubleshooting flows, I come over here, I'm going to see 2 flows here. One is 501 and one is 500. If I refresh here, I should see that now I have 1 packet that matched the 501 rule, which said allow it, so it's top down. So I could create a rule, a flow that overwrites the other flow. Okay, let's come back here. And I'm going to delete these flows because I'm going to delete the flows with OVS, OFCTL commands. I'm going to delete those flows. Okay. So now if I go back to my switch and I look and I dump the flows again, see that the flows are gone. The 501 and the 500 flow are gone. Okay. I can set up iPerf on a host. I can then, from the other host, I can then call iPerf. So I'm binding H5 to that its IPv6 address, and I call from H1 to connect as a client to that IPv6 address. I'm generating, 5 meg of traffic across it. Okay. So we can also go in with the OpenDaylight controller and create flows manually. You can say go in, add a flow called like H5 toss. We can select the node we want to set this up on. We can set the input port, 1. We can set a priority. We can change the type to 86DD. We can set the source address. We can set the destination address. And we can then come back down here. We can change protocols and stuff. We can set an action, modify the toss bit, set that to 46. And then we can also set an output port to port 2, add the action, install the flow. So we have a flow here. We see that it's installed. We can then go to our switch and see that now we have a flow installed in our switch. We went into the GUI and we created a flow. The other way we can create flows and deal with this is to use Well, we can also set up web servers on the little clients here. So we can set up a little web server. I've got this little Python web server that runs. And we can have the systems creating HTTP traffic between themselves over IPv6. And we can that. And then I can have like H1 do a wget on that v6 address, and you see the page loads, just a little smoke page. I can also interact with the switch through the web interface. So the northbound API with OpenDaylight is a REST API. So I can do curl commands. So if I wanted to go to OpenDaylight, whoa, okay. Let me show you what I did here. I did a curl command, sudo curl, and I look at a particular REST-conf, operational, OpenDaylight inventory nodes, node 1, OpenFlow :1, and I get back all this data in the web that then I can parse and create programs on. I just did a get on all this data, you know, I can get back. And I can do curl and stuff, and I can create flows this way. I can, let's see, I can create a flow, I can delete a flow through the curl interface. The other thing I can do is I can start a utility that I use called Postman. Let me show you how that works. To interface with the, I install this little free utility called Postman that runs, that allows me to interact with the REST API of the OpenDaylight controller. So from REST, I can go into, I can type in a particular URL, do a get, and I have to set some basic authentication. I have to log into the controller with a password, set the content type to application XML, and I want to accept XML. I send. Oh, that's not it. This is what I want. I was putting a curl command into, that's what I want. So I'm going to call this particular URL of OpenDaylight, and I'm going to do a get on it, and what I get back a status 200 OK, and then I see my switches here, because I'm looking at nodes. And based on the URL, I can get information, I can get flow statistics, let's say, from the device, and this just shows me how I would interact with the REST API and get data from it. The other thing I can do is I can create flows. I know we're running out of time here. So I'm going to show you how I'm going to create a flow with the REST API. So here I'm going to call REST for this particular OpenFlow controller or OpenDaylight controller, OpenDaylight, inventory nodes, OpenFlow, and I'm going to create a flow with the number 124. And instead of doing a get, I'm going to do a put. And I'm going to put some raw data in here. And what I'm going to do is I'm going to create a flow. So I've kind of pre-scripted this, of course. So I'm going to create a flow, and it uses this particular format of the flow. And I'm going to take traffic from 20::4, and I'm going to give it a name, and I'm going to block the traffic, and I'm going to hit send. Send comes back with 200 OK. And if then I look at my OpenDaylight and I see this, I see my flow. So through the REST API, I interacted with Postman. I created a REST command. I did a put on the controller, and that controller then took that and pushed it down to the switch with the southbound API. I can create, I can delete that. I can create a v6 flow. So I could go in and in Postman, I can create a different kind of a flow. I can create a different flow on a different switch. Like we'll go to switch number 3 here, and we'll create a flow number 12. And then I'll do a send, and I get 200 OK. And then we'll come back here, and we'll look at switch number 3 flows. And you see now that I've instantiated a flow here. So you can see that you can interact with the REST API to make flows. And I think that people aren't going to really log into the OpenDaylight GUI and create flows. They're going to use a programmatic interface to create flows in the environment. It's going to be a virtual machine or an application that sends that HTTP request to the REST API to request some type of connectivity from the network. And so it's more often than not, that's how this is going to work. And so that's how, you're going to create a Python script or something like that to then build the flows on the network and then build the open flows. And we have connectivity end to end. So we are out of time. So, your chocolate and your peanut butter can go together. You saw us start up MiniNet. We started up OpenDaylight. Started the controller, we started Wireshark, you could see the open flows. We built the topology, we could build flow setups, we could observe the traffic. So if you wanted to collaborate more, just contact me and we can work on that. So thank you very much.
There are refreshments upstairs. Scott, did you want to try to take a couple of questions? Or
I could, but I know that people need to stay on schedule. I apologize that went a little longer than I expected. Yes.
Quick question, Scott.
Yes.
How much additional delay do you anticipate is going to introduce to the normal forwarding? I mean, we're doing this on a per flow basis, on a particular application, trying to set up a path perhaps across 20 nodes, given all the information we need to collect, all the rules that we have to push out, to try to make this one as transparent as possible to the user. I mean, how much penalty are we going to? I mean, do you see this done at the flow level? Perhaps it's going to be more like a traffic engineering tool, at the core provider. I guess, what's your opinion on that?
Any of those use cases could be scripted in a way, and a script could be built with the northbound API to create any kind of a flow or policy that you would like. Drop certain kinds of packets, forward certain kind of traffic based on different characteristics. The speed with which that takes, it happens very, very fast. It's just a single packet from the controller down to the switches to put that in their flow tables. Happens very fast. This is just running on a little, Intel-based laptop here, so this isn't probably hardware that you would go and implement in production, but it's a way to start and learn how this works. I think if you had a requirement to start up, 100,000 flows in 1 second that didn't exist previously, it may take more time it may take, a tenth of a second to instantiate a flow. But once the flow is built, it's built. Then forwarding takes place in hardware on the switch, not based on software. It's in the policy. The network element can then make a local lookup in its flow table of how to forward the packet. Not every packet goes back to the controller, maybe just the first one, or as the policy gets built, then the controller communicates southbound to the network elements. That's the only time when there would be a delay. And then we're also leveraging the Intel-based platform at the edge to make decisions of forwarding. So very fast processors, compared to the small emaciated processors in many routers and switches of today, because they have so much distributed work to do.
Just a quick question.
Hold on.
The concept of policy decision points and policy enforcement points considered in how you're developing policy and pushing policy and enforcing policy down at the agent level? Anything like that?
That's up to you. I think the only limitation is your imagination and what you can script to build. So your security policy would dictate what the policy would be for the flows. And you could set it up where if there's no flow, the packet gets denied. So it follows the security golden rule, that which is not permitted is denied. So there's some inherent security in there. Basically, every network element is essentially a firewall implementing that default stance policy. But you can create specific drop rules and specific allow rules in an order and use priorities like an access list to create that ordered list. Yes.
Thank you, Scott.
Okay. Thank you.